Hey guys, so our new topic, we're going back to some calculus now, and more specifically over the next few weeks we're looking at differential equations. And these come up a lot, especially when you get to university level calculus. In fact, you've actually seen a lot of them before without realizing. So first of all, copy the notes down in your book as we go, pause the video when you need. So the first heading I want you to put today is what is a differential equation, and let's talk about what it is. So a differential equation is just an equation that is written in a form of a derivative, whether that be the first derivative, second derivative, third derivative, or so on. It's a differential equation, okay? So it's when you have the derivative of one term with respect to another. So when they call a differential equation a first order differential equation, it's just the first derivative. So second order, second derivative, and so on. So there's an example just there, dy dx equals x squared minus 3. That's a differential equation. Now if a question says, and there's some in your exercise, to solve the differential equation, it just means find the original, okay? So solve it for y, or depending on whatever letters they're using, but in this case I would solve my differential equation dy dx for y, which means I know I solve that by integrating, okay? So when I integrate, hopefully bringing back your integration skills are okay, and then always we have that plus c, okay? Now if a question mentions a point, okay, so if it said solve the differential equation and it gave us that original example and it said when x equals 0, y equals 4. So it gave us some point, then we know that we can find the value of c. And you would do that by just subbing in x being 0, y being 4, and then you'd find the value of c and then rewrite it, okay? So when they do give you a point or enough information to be able to substitute in, you need to find the value of c. In this original case though, we'd leave it as plus c as we weren't originally given those points. So that's all a differential equation is. Nothing new, nothing different to what you've actually seen before. Okay, so next heading in your book then. Now today we're specifically looking at slope fields, okay? And these are brand new in the course. And I think to an extent they don't do a lot. In fact, you know more things at the moment that help you more than slope fields do. However, they're in the course now, so we will look at them. The first thing I want you to do is go back to about a year ago from now when you looked at sketching derivatives, okay? So I've given you two graphs here and they look very similar, all right? I want you two cubics, I want you to sketch the derivatives. Now, pause the video, give it a go. One thing I always do when I sketch a derivative, and I guess it depends on how you got taught, but I do my derivative sketch straight underneath. Okay, so we're sketching the derivatives. So pause the video, give it a go, but if you can't remember, I'll do the first one with you. The way I like to do these is I think, okay, if I'm sketching the derivative, I got positive above the x-axis, 0 derivatives on it, and negative below it, because remember I'm sketching the graph of the derivative against x. So the first thing I do is I label my original graph all the gradients. It's positive, it hits 0, then it's all negative here, hits 0, and then it's positive forever after that. Second thing I do is transfer my zeros down. So a 0 gradient, because it was flat there for a second, so it must hit my x-axis of my derivative there. Again, 0 gradient here, so it hits my x-axis. So I know it passes through those 2 points on my derivative graph, and then it's just a matter of saying, okay, well it was always positive on the left-hand side of that first 0, so it must have been up in the positive region. Then all in between those two zeros, it was a negative gradient, so it's a negative. And then after that, it goes back positive again, so then we have this. All right, now do it again for the next one. What you will find, or you should find, is that when you do this second one, you should get the exact same graph as the first one. And there's a reason for that. The reason is they're actually the same cubics But the original graphs are these same cubics, but they have a different constant, shifting one up higher than the other one, okay? So they both gave me the same derivative graph. Now let's think for a second. I really want to just get this deep understanding here, which is why I'm showing you this. Let's think about what the equation of my derivative graph here is, okay? So my equation of my f dash of x graph, or dy dx, whatever you want to call it. Well, the two roots are -2 and 1, which means that this graph, dy dx, is going to be, if I write it as roots, x plus 1 and, oh, and I just realized I put a negative there when it should be a positive one. So, okay, sorry, that makes that a -1 and a +2. So I can find the equation of that parabola by just expanding, and when you do that, you get this equation. So now I know the actual equation of these derivative graphs here is x squared plus x minus 2. If I integrate that equation now, so that's a differential equation because it's in the terms of its derivative. If I integrate that to get my original graph, which is my original cubic, let's see what I get. X cubed on 3 plus x squared on 2 minus 2x plus c. Now, notice if I start with my derivative and now I integrate, I get this, which is both of these original graphs here, because the plus c is just shifting it up and down, okay? So depending on what c is, depends on what the original graph is, whether it might be the first graph or the second graph, which then leads me into my next point here. Really, without knowing the value of c, there's infinite amount of possibilities or an infinite amount of those cubics I could have given you that would have all produced the exact same derivative or differential equation. So imagine every single type of cubic that I could have given you, and my drawing's not great here, but all depending on the c value, okay? Whatever that c value is going to shift those cubics up and down. So the point I'm getting at is, what we end up with is, with a differential equation, if we want to sketch its original graph and go backwards, there's multiple versions, okay, depending on what c is. Now this actually then forms what we call our slope field, and that's the whole idea. If I was to then draw a slope field, so the slope field represents all of the possible differential equations that satisfy the question. And what they actually do to draw a slope field is they put the gradient, so they're all tiny, tiny little tangents. And again, my drawing's not great here, but they're all little tangents which are describing the gradient. So each column would obviously have the exact same tangent, which I'm trying to show here now. And you end up with, we have a flat, a flat, a flat, and a flat. You end up with all these tiny, tiny little dashes as little columns, and that is a slope field. So let me show you a nice drawing rather than just mine. Here's one. Here's a great example, much nicer than mine, of the slope fields. Okay, so you can see here, if you follow this rough idea, you could sketch the graph of it. You can, if you followed it down long enough and following all those tangents better than me, you can sketch the graph. But again, see how there's many, many options that you could do. Depending on where your starting point is, you're connecting all those dashes on your slope field. Which brings you back to this. So, the reason I've just shown you that is I really want you to see that deep connection, why there's those infinite solutions, and it's because of that plus c, depending on what it is. Okay? Alright, here's an example question that you might get, and I've just taken this straight from one of the exercise examples in your textbook. So it wants you to start by drawing the direction field. So if we get asked to draw the direction field of that, it's as simple as just plugging some points. Remember, your direction field are the gradients, okay? They've given us our first derivative, which means that's all in terms of the gradient, because we know that's what the first derivative represents. So the first thing I would do is just sub in some points. Let's start by subbing in x equals 0 into our derivative. When we sub in x equals 0 into our derivative, we get 0, which tells me, and I've done that one already, on the values where x equals 0, so the y-axis, there is a 0 gradient, which is the perfect horizontal lines. So now let's test x equals 1. When we sub that into our derivative, we get equals 3. Now we know the number 3 is a positive gradient. That is quite steep. Remember, the gradient of 1 is our 45-degree angle. So at our value of x equals 1, we have this rough gradient of 3. So then you do the same thing. What about x equals 2? Well, dy dx is going to be 6, so it's going to be quite steep, which then gives you a forecast into the future that every single x value that we're going to increase by, our gradient is going to get steeper and steeper and steeper every single time, all the way closer and closer to being a vertical line, but never will become one. So then the same thing when we sub in negatives. Okay, if I sub in -1, I'm going to get my gradient of -3. And that's how we conduct our slope field. Again, it seems like a lot of work, and yeah, I won't comment anymore, but you can see how they work, and there, once you complete it, you would get your slope field in total. So it's just about subbing in points. So now it says find the graph of a function that passes through the point 0, 1. So what that means is this actually, if we graph the original function, it has multiple possibilities, because let's think about our integral of this. If we solve that differential equation, it would be 3x squared on 2 plus c. So there's all our possible values, okay? A parabola that is getting shifted up and down depending on what a c value is. So that's where you get the multiple different parabolas depending on where you draw it on your slope field. But this question in particular has given us a point. It's told us that this parabola passes through the point 0, 1, which I know it passes through here. So it says find the graph of the function, okay? So it's just getting you to sketch, following your slope fields, the graph of that as best as you can. Okay? Remember, when you hit one of those, they should be a tangent to your curve. All right, so there's part B. So then part 3 says now use calculus to find the equation. So I already integrated, and when I integrated before, I got a value of 3x squared on 2 plus c. Now they've given me a point, so now I can just substitute that point in. So x is 0, y is 1, which gives me that c is 1. So therefore, the equation of the original graph is that. And that's it. So it's using a lot of skills you already know and just looking at this new idea of a slope field. Okay? So to draw your slope field, it's just about subbing into the gradient function. And that's it. So I want you to have a go at the exercise today for this lesson, and 1301. Okay? So I will write on the bottom of this document, and I'll upload this document onto Compass, which exact questions I'd like you to do. You can always do more than that though.